Welcome, everyone. It is my great pleasure and honor to introduce our keynote speaker for this afternoon, Professor Arun Majumdar. He is J. Precourt Professor at Stanford University at the Department of Mechanical Engineering. Prior to joining Stanford, he was the Vice President for Energy at Google, advising the company on its energy strategy. He still consults with Google. Before that, in 2009, he was nominated by President Obama to become the founding director of ARPA-E, the Advanced Research Projects Agency in Energy. He served until 2012. His honors include, but are certainly not limited to, memberships to the National Academy of Engineering and the American Academy of Arts and Sciences. So he is a leading researcher on the science and engineering of both nanoscale materials and devices, as well as large engineered systems. So I'm really happy to be able to introduce him today. So please, everyone, join me in welcoming Mr. Professor Arun Majumdar.
Well, Hugo, thank you for the very kind introduction. And I want to take this opportunity to thank Karina and my former team at Google for inviting me out here. This is my first time in this meeting. I've been sitting at the back of the room listening to some beautiful presentations and theorems and algorithms and solutions. What I'm going to do is to not give you any solutions. I'm going to pose problems. And hopefully you can bring your solutions to these, I think, really important problems. So I'm going to talk about energy infrastructure. And out here, as you can see the picture, this is called the greatest engineering achievement of the 20th century by the US National Academy of Engineering. The key word out here is the 20th century. And I'm going to talk about some of the issues that we are having today that really does not or does require new thinking for the 21st century. Well, this has been enabled by this. This is the transmission network, electricity network in the United States. It is a mesh network. And this is the lifeblood. These are the arteries and the veins of the United States. If something happens to this, life comes to a standstill, as we have seen in the recent past through various storms and other things. Now, if you ask that question, what's the architecture of this network? And it goes to the paradigm that has been developed for many years. And the paradigm is the following. You have centralized electricity generation. You have long-distance, high-voltage transmission. You have medium voltage, local distribution, and then you get your electricity to your homes and buildings from the feeder lines that you have in your neighborhoods. That's the architecture. And that architecture goes back to Tesla and Edison, when the first electricity was from Niagara Falls to New York City, high-voltage transmission, and then local distribution. And as you can see, this was the paradigm, again, centralized generation. The reason centralized generation was developed was because it was cheaper. Because thermal power plants, you get economies of scale when you make them big, and so that's why they're centralized. And then you have one-way power flow through the grid to the distribution network, which is the branch network, down to the loads, and you have zillions of loads. So that's been the paradigm, and that architecture has not changed for 120 years, even though the devices have changed. So to appreciate some of the problems, it's very important not just to understand the technical aspects of how it operates, but this paradigm that I just showed you has lent itself to institutions and markets. And it's very important to couple the technical aspects to the economic aspect because they cannot be decoupled. So I'll very quickly go through how is it structured, how the institution structured, and how does it operate. So this is how it operates. You have the long-distance transmission, which is what is called wholesale electricity. And they are managed by organizations called system operators, independent system operators. And I'm using this example of California as an example. There are similar things across the United States. These are wholesale markets. California ISO, independent system operators, they handle the high voltage transmission, and it covers not only California, but it covers the neighboring states as well. So these are interstate things, which means the federal government has to be involved in it, which is what is managed by FERC. FERC is the Federal Energy Regulatory Commission. Then this is called a market because people buy and sell electricity on a daily basis. Some of them are utilities like PG&E is in the Bay Area. That's a utility. There's Sacramento Municipality, the Southern California Edison. These are all acronyms that you see out here. They buy and sell electricity, but you can sell electricity from a centralized natural gas generation plant or a wind farm, and they can also sell electricity. So it's really created like a stock market. As I'll soon say, this is not quite a stock market, but that's where it does trading. It buys and sells electricity. The electricity is sold to the utilities who are responsible for local regions. And these regions are a monopoly, and that's why they're regulated. But they're regulated by the State Utility Commission. They don't cross state boundaries. And so you have PG&E, for example, in the Bay Area, buying an electricity. They also sell electricity, the wholesale market, but they buy from the wholesale market and distribute it to your homes and buildings and factories, et cetera. And that's called the retail market. And because it is only located within one state, it comes under state jurisdiction, which is the Utility Commission. I'm giving you all these details because it's important to understand not just the scientific and technical aspects, but the business models as well, because they are interrelated. So it turns out that, contrary to what many believe, utilities do not balance the grid. The balance of the grid is that generation and the loads are balanced in real time. There is no storage today, not much. In real time by the wholesale market, by the independent system operator, grid operator. And how does it do that? Here's how it does. You are buying and selling electricity. If you go to a place called Folsom, California, which is near Sacramento, they have all these panels out there. They're watching it in real time. And it turns out that the electricity that is delivered today was planned out, most of it was planned out yesterday. There's a load estimation algorithm that happens. And so you have what is called a day-ahead market based on the estimate that is done a day ahead. Well, when the real load comes, it turns out that it's not exactly what is predicted the day ahead. So then you try to correct it with smaller knobs, which is called now the 1-hour market, the 15-minute market, the 10-minute market, and the 5-minute market. These are all fine-tuning so that you can get to the load exactly, because in the day ahead, you cannot quite get it there, get it to the real thing. So as you can see, this is not real time. It's not like the stock market. So just to give you a separation of time scales, which is very important to understand the dynamics of the system, these are on the x-axis, on the top, you see all the time scale. The 16 millisecond is one cycle, 60 hertz cycle. Below that, there are faults that happen that can cascade and bring the whole grid down. And we really don't have much control over it. Then you have the 16 millisecond, over a second or so, what is called the frequency regulation, then 5-minute, hour ahead, day ahead, and the long-term planning for most utilities is called the asset planning. That goes out for more than a year, 10 years time frame. So the most important thing that is done today is the load estimation. And I'm not sure very sophisticated techniques are used for the load estimation today. I'm sure you have many techniques that are much better today. So why is that done? How is that done? Well, the day-ahead market, the day-ahead load estimate is done by history, by weather, etc. Then there's the hour-ahead market, then the 60 hertz. 60 hertz, by the way, the frequency, is a proxy for load and generation imbalance. Because there's too much generation, the frequency goes up. There's too little generation, the frequency goes down. and the ISO, the grid operator, tries to keep the frequency at 60 hertz plus minus 0.035 hertz. That's the tolerance level. And so there's a real-time control going on, but it turns out that based on the day-ahead estimate, 95% of the load is dispatched. And the dispatch happens according to price, or what is offered, but the bids. So you can have 300 megawatts or 60 megawatt hour, $60 a megawatt hour. All that 300 megawatts is dispatched for the next day. Then 400 megawatts at $75 a megawatt, and keeps on going. And so you got 95% of the load that is dispatched in the day ahead, then you got about 4% at hour ahead, about 1% at 60 hertz, and that's how the grid operates today. And just to give you an idea, this is a typical day in California. I picked January 13, you could pick yesterday, and you'll see something similar. And what you find is the actual demand that you see, the solid line, and the dashed line, which is the day-ahead forecast, that is, does a reasonable job, but at times it's off by about 2 gigawatts. And so that is corrected by the hour-ahead demand forecast, which gets to about a few hundred megawatts, and then it goes down to the frequency regulation market, which is sort of on the order of a second, that happens in a few megawatts. That's how it works. And as you can see in the bottom curve, you actually take a note on the load curve, it sort of flattens in the middle of the day, and I'll tell you exactly why that is happening. And then you find on the bottom half is what the renewables are doing. And as you can see, the solar has a peak during the day, as you can imagine, but it's actually fairly predictable. People think that solar is not predictable, but these are utility scale solar, which is generally put in the middle of the desert. You're not going to put solar in San Francisco. It's a very bad idea. But you put it in the middle of the desert, and you know where the sun is going to rise and when it's going to set. What is unpredictable, not very predictable, is wind. I'll come to that in a minute. So as you can see, the wholesale market the wholesale electricity is determined, the prices and the dispatch are determined by what are called the markets, the wholesale, the day-ahead, hour-ahead, 15-minute frequency regulation. And that's how the prices are determined. On the other hand, what is at least done today in California, for example, in many parts of the country, the retail side, the prices are fixed, mostly, 90% are fixed. So there's really no correlation between what is happening at the retail price and what is happening at the wholesale price. The wholesale price is dynamic, and we are all paying in PG&E fixed prices. And the fixed prices are within a month. If you cross tier 1 to tier 2, your rate goes up from 13 cents a kilowatt hour to 15 cents. And when it goes from tier 2 to tier 3, it goes up to 32 cents a kilowatt hour. And we have no idea when we are crossing over. That's the state of the art today. So I'm going to show you some emerging trends that are happening. And this is where the coupling is taking place. And I hope you'll appreciate some of the issues that are arising. So emerging trends is that, number one, the biggest transition that has happened over the last several decades is that natural gas, thanks to Canada and the United States and Mexico, natural gas is abundant and it's cheap. And more of that is being used for electricity. There's a huge transition that is happening from coal to natural gas, primarily because of economic reasons. So what we are finding is that the electricity network and the gas network, which you can see the network on the right-hand side, is the gas pipeline network, are getting more and more coupled. And that's a good thing because it's bringing the price down. Well, let me show you what the problem that are arising. And this is data from the New England region where the pipelines are limited. It's very hard to get pipelines in there. And what happens is that you see these spikes happening. These are when the really cold winter happens. And the last spike that you see was the polar vortex. And so what happens is that in a cold winter, people want to heat up their homes, the demand for natural gas. Well, you don't have enough throughput in the pipelines, so the natural gas spot price goes up because the supply is limited and the demand is high. But because a lot of the electricity is being generated from the natural gas, the electricity prices go up. So you have these huge spikes that are happening where the spot price goes up by a factor of 5 to sometimes 10 times the average price. And as a consumer, I would have to pay that 10 times the price not only for the natural gas for heating, but for the electricity as well. The question is, coupling is great for reducing the price on an average, but sometimes they're not good. So you need to decouple. The question is how best to make that happen. We don't know yet. So this is on the winter. Let me tell you about this summer. And I'm going to show, and you all know about what global warming is. Things, the world and the earth is warming. And we all know that we have warmed about 1.4 degrees on an average since the beginning of the Industrial Revolution. Well, that's the average. People forget about the distribution. And I'm going to show you the distribution, which is the deviation from the average. And as you can imagine, some summers are hotter and some summers are cooler. It just happens that way. But it's important to note where that distribution is going. So here's the data. Initially, you see a smooth curve, Gaussian curve. And the red is the hotter summers, and the blue are the cooler summers. And see how this is data from the 50s and 60s. The distribution, this is globally averaged. So this is what is going on. So clearly, the average has moved, but the tails of the distribution are reaching 4 to 5 times the standard deviation at probabilities that were completely unheard of in the past. And this distribution ain't moving the other way. It's only going in one direction. This is really important for the energy infrastructure because the tails of the distribution have a disproportionate effect on the grid and the energy infrastructure. Because when you have really, really hot summers, your air conditioner, everyone turns the air conditioner, and there's congestion, and this throughput capacity is, you're just limited in that. So how do you handle this situation? Well, this is one emerging trend, the coupling and the decoupling. The other one, at least in the United States, I don't know enough about Canada, at least in the United States, age and security are turning out to be huge problems. Let me give you one example. You see these big transformers that you are near the substation in your neighborhood. The average age of these assets, there are about $1 trillion of assets on the grid. The average age is 40 years, or today, the life expectancy is 40 years, the average age is 42. We are at -2 on an average. Let me give you another example of what's going on. This is an event that happened close to where we live. This is San Jose, you can see in the north, Morgan Hill on the south, and in between there's Highway 101. Those of you who've been in the Bay Area know this. And along the highway, you'll see a huge substation called the PG&E Metcalf substation. Well, at 2 a.m. in the morning on April 16th, there were some few gunmen who took some guns and shot at the radiators of these cooling units for these transformers and leaked 50,000 gallons of oil. Not only that, 15 minutes before that, they sheared and they cut the fiber optic and telephone cables so that 911 was disabled. And no one had heard about this. You know why? Because this happened the same evening as the Boston Marathon bombing. So we have not just a cyber security issue, there's a cyber physical security issue as well. So these are some emerging trends which are not pointing in the right direction. There's some other trends. We are finding that the cost of, this is the economic trends now happening, the cost of electricity generation from wind, which is these blue bars, have come down to the point that it has actually really flattened out. It's getting a little cheaper, but it's sort of flattening out. And it's very important to note, and by the way, the adoption, the green curve, has just gone up exponentially. The reason this is happening is because now it is cost competitive with the cheapest way to produce electricity, which is natural gas. And so now they are comparable. The wind is actually cheaper than coal. However, it is intermittent. The blue thing, the title, is very important. It's intermittent. And but wind is still centralized. You still have 5 megawatt wind turbines that you put on the transmission network. What is even more interesting from a technical point of view is solar. Because solar can be both centralized, like a big solar plant, utility scale solar plant, and distributed and intermittent at the same time. And what is happening in solar in terms of cost? As you can see, the cost is coming down. When I was in DOE, we launched something called a Sunshot 2020. Just like President Kennedy had moonshot to go to the moon and return safely within the decade, our goal was not to go to the sun and return safely, but to reduce the cost of electricity to 5 cents a kilowatt hour, the cheapest, without subsidies, within this decade. And what we are finding, these blue boxes, or sorry, the green boxes at the end, is the utility scale cost of solar that is coming down, and that is comparable to will be comparable to wholesale natural gas electricity cost within this decade. And what we're finding on the gray bars that are vertical in 2016 are the distributed, that is the retail end of it, and that is within the price range of retail price electricity. And so suddenly you're finding, for the first time in 100 years, that distributed generation could be as cheap as centralized generation, and the whole paradigm of the Tesla Edison grid goes up and down now. It's upside down. And so the question is, how do we manage this? We are seeing the effects of that today. So this is, once you start putting electricity generation units at the edge of the network and not in the centralized, on today's grid, this is what's going on. You remember the California load curve? In the middle of the day, it's flattened, and then it sort of peaks up. It peaks up in the evening because people go home, turn on the televisions and the microwaves, etc. But this is what is going on, and this is what is about to happen. That the load in the middle of the day is going like this. It's dipping. And then the ramp up in the evening is even stronger. This is what is going on, and this is called the duck's belly. It looks like a duck, and the duck is getting fatter. And the ramp up rate in the evening is about 150, 200 megawatts a minute. We really don't know. The grid operator doesn't know what to do with this today. And what they're trying to do is that in the middle of the day, they want to put negative pricing. Because they have excess electricity and the load goes down, they want to put negative pricing. They will pay someone to take the electricity away. Imagine if you had a large battery. That's good arbitrage out there. But we don't have that in a cheap. Why is this happening? The reason it's happening is because of this. It's rooftop solar. Because once you start generating at the edge of the network where the loads are supposed to be, it's essentially a negative load. And now you have an instability in the grid, which is what has happened in Germany because they put so much solar that the grid gets unstable. And so now we have to figure this out. Now, one of the things that can help is storage. But storage is expensive. It's getting cheaper. So this is the cost curve of the lithium-ion battery that is coming down, and the blue bar that you see at the bottom is lead-acid battery. So not only is it going to get as cheap as lead-acid battery within this decade, the number of cycles that you can get out of it and the longevity of this is much better than lead-acid battery. So this is the future. In addition to that, when I was in the Department of Energy, we funded a whole bunch of new, innovative, breakthrough technologies that are now in the piloting stage coming out of startup companies. This is happening. All kinds of different kinds of batteries. I won't go into the detail. So if you step back for a moment and think about the whole system, here's what's going on. The current paradigm is the following. Again, centralized generation, one-way power flow to zillions of load. And on the centralized generation and the long-distance transmission, you got independent system operators with wholesale pricing. Then you got the electric utility, then you got your homes. And what you have is that the wholesale price, depends on a market, day ahead, hour ahead, 15-minute market. And let us say, as a hypothetical example, the price is 7 cents a kilowatt hour plus minus delta. And the delta is because it's a market. On the other hand, the utility commissions design the rates in such a way, let's say 15 cents a kilowatt hour, so that it's always higher than the wholesale price. Because otherwise, Enron kind of things happen in California, when the wholesale price went higher than the retail price, and then the utilities go bankrupt. So the idea for stability, the regulated retail price is always higher than the market-based wholesale price. And that's the guesswork that the utility commissions have to do. That's how it works. Now here's where the shifting paradigm comes. You got this 7 cents a kilowatt hour plus minus delta, which is the wholesale price, and you got 15 cents a kilowatt hour that the PG&E or some utility is trying to sell you. But guess what? Let's say I figure out a way to put solar on my roof at 10 cents a kilowatt hour. Now, I'm producing electricity at 10 cents a kilowatt hour, and I could sell, if possible, to the utility at 15 cents a kilowatt hour. That's called net metering. Okay? So I can make money. What happens to the utility? Well, we don't know. You can have storage as well. Storage is getting cheaper. Imagine now, let's say 10 years from now, which is not a very long time as far as electricity and energy infrastructure is concerned. 10 years from now, this could very well happen. It's happening today. And let's say you have natural gas coming into 60 million homes in the United States, and there are now technologies that are coming out that can take semiconductor devices and produce electricity in your water heater and use the waste heat for your water heating. This is happening, and that could happen at 7 cents a kilowatt hour. Now you ask the question, how does this whole system behave? How will the utilities, will the business models have to change? You get an architecture something like this. You certainly have centralized base load generation, and you have centralized intermittent generation with solar and wind. You may have some centralized storage as well, but on the edge of the network, you don't just have loads anymore. You have storage, you have generation, and you have other entities as well, all coupled together. Now the question is, will the business models have to change? Will the system have to be operated differently? Here's the shifting paradigm. For the past 100 years, we had centralized baseload generation utility, which is the utility, and follows distributed variable load. The generation always followed the load. You flipped on a switch, someone had to turn on a generation. You didn't care about it. But now you have centralized generation, baseload, and intermittent generation, plus you got distributed generation, storage, and load, which is a prosumer. It's a producer and a consumer. Who leads? Who follows? Who pays? Questions are unanswered. The wholesale price in the utility always lower than the retail price. The utility makes margin that way. Well, cost of distributed generation, which is the consumer level, could be lower than the retail utility price. Isn't this an instability? Well, perhaps, unless you change the business model. And finally, the consumer has single option. In the past, for the last 100 years, we had a single option for electricity with essentially no transparency in cost, which is a one-way power flow. This used to be that single telephone line to your home. Well, now we have telephone line, we've got wireless, we've got all kinds of satellite, all coming to your homes. And that is what may be happening in the electricity side as well. And the question is, consumer has multiple options for electricity. How does he or she minimize the cost? How does the system balance with two-way power flow? And who is going to do this in your home? And these are questions that are still open. We don't know yet. But these are long-term issues that have to be dealt with. So let me give you some offerings of what should be happening. So in terms of the centralized base load plus intermittent generation and storage, this is the paradigm that I showed you earlier. And this is centralized. There's nothing to do with the edge of the network. This is still centralized, but intermittent. Now, if you have 95% of the load or the generation dispatch a day ahead, which is very incompatible with wind, for example, because you cannot get 300 megawatts exactly in wind. And this is the problem that is going on. Either you predict the wind capacity exactly at 300 megawatts at $60 a megawatt hour, or we have a problem in this, and thereby if 95% of the generation capacity is dispatched in a day ahead, typically wind and solar will be very hard for them to go up beyond 5%. And so what really needs to happen is the operation of the grid has to go from 95-4-1 to something like 70-25-5. And that operation, which means you got to get more and more real time, which means you need information, which needs data. You need communication. It's going to go away from the load prediction, everything following the load, to the load following the generation, which means you need communication, fast communication on the order of a few seconds. Now, a few seconds for most of the people in Google and Microsoft and all, is nothing. But we are talking about a system where the inertia itself is on the order of that. So we should be able to do this but the ideas of latency and other issues are important. So this is what ought to happen at the centralized dispatch level. What about the edge of the network, which is even more interesting? So you have the centralized, now you got the centralized, but you got the distributed at the edge, which is intermittent in itself. Now what you do, it's an even higher level of complexity. And here's an idea which I think a lot of people think that might happen, but we don't know yet. So here's the architecture. The architecture, you still have the legacy grid. You still have centralized generation, and you want to operate it with 75-25-5 that I just mentioned. But now you got assets at the edge of the network which are generating and storing electricity. And the way one could perhaps think about this is, could we define a microgrid of some kind that can connect with the legacy grid or can disconnect with the legacy grid when needed? And there could be now an array of microgrids connected to in some level of hierarchy. And to be able to do that, you need to be able to put switches. You need some electronic power transformers, electronic conversion, as opposed to the old Tesla Edison, the transformer that you had. And now that you have electronic conversion of power, you can put intelligence, you can put networking. So imagine these blue circles as electronic power conversion units and the yellow squares as some kind of a network computing, distributed network computing. And you could then look at these microgrids. If you have to disconnect from the legacy grid, there are some disadvantages. Who's going to control your 60 hertz? Who's going to control your voltage at 120 volts? Well, that has to be done in an autonomous way. So local autonomous estimation plus optimal dispatch, because you want to minimize the cost of load generation and storage, still needs to be figured out. And we still don't exactly know how to do this for electrical power circuits. And then, of course, you have the long term. These are short time scale if you want to disconnect. The long time scale, you have the cloud, which is wonderful. It minimizes the cost. It connects. It provides connectivity in some way. But then it's, you can connect these units to the cloud when necessary. You can collect data. You can do all your machine learning, figure out how the consumers are behaving, have better estimates of loads, et cetera. But it's very important to keep that autonomous part there, because if you have latency and you have 60 hertz issues and you have faults that are time scale less than 16 milliseconds, you have a problem. And so having autonomous intelligence combined with the cloud level intelligence, very, very important. So here's, if you step back for a moment again, here's what I think is going on. You have geographically distributed and dynamically coupled networks. One is the electricity network, the other is the gas network, which is molecules, and you got information network, which is bits. We really don't understand the dynamics of this network. This is not off and on. These are, there are many questions that are unanswered. How can we design resilient coupled networks while minimizing the cost? And these are not digital networks. These are, things where energy and masses are conserved. You have, how can we understand and control system dynamics from sub-cycle to seasonal timescales? We don't know yet. And again, there are latencies, there are time constants, there are resonances, the energy and mass conservation over networks. There's electromagnetics. You got to solve Kirchhoff's law and Maxwell's equations sometimes over the networks. And you got capacity limits and congestion. How do we do that? And finally, how do we prevent catastrophic failure? Can we figure out ways to figure out how close are we to a cascading failure? And if you can find on a dynamic network, which has all this energy, mass, conservation, et cetera. Just to give you an idea, when you have a link in a graph, if a link fails, then that power, by the way, in a transmission line can be rerouted automatically. We don't have control. We don't have routers for electrical power. Power flows from high voltage, low voltage in a mesh network like water flows down a hill. It flows anywhere. We really cannot control power. So the idea of power routers to be able to really determine where it should go deterministically cannot happen today. So these are the challenges that we have. Again, this is the United States. I told you I'll pose problems for you. Here are some of the problems. Let me give you an even bigger problem, and I'll with that. This is the population density of the world. You can see where the people are. And I'm going to show you, overlay on top of that, the lights. This is where the electricity is. And what you find is there's a big mismatch. There's a lot of electricity. There's a lot of in the United States and Canada, really bright, and we want to make it brighter in a sustainable way. But there are many parts of the world where people really have not turned on the lights yet. And we need to figure out ways to enable them to turn on the lights, hopefully within our lifetime, which was my goal at Google, to create the technology to enable people to turn on the lights in a sustainable way. And just to give you some numbers, there are 3 billion people today who have either no or very limited access to electricity. 3 billion, which is almost half the world's population. And in the next 40 years or 35 years, additional 2 billion people will be added to the same regions that have marginal or no access to electricity. So half the world's population. The population is growing faster than we can electrify. That's the problem. And I think the idea, for the first time in the history, the distributed generation like solar and storage and all getting cheaper than centralized. So do you really need the massive grid to be strung, the Tesla Edison grid? Or would you like to create a fully automated microgrid with distributed solar and storage and load control for optimal dispatch? I think that'll be a key enabler. But how to do this is still up in the air. So let me stop here. Thank you very much. Happy to answer some questions.
We have plenty of time for questions. There are mics in the alleys. If you have questions, just go ahead. Yes.
So I'm here. Okay. Yes. So a lot of the problems that the electric grid is going to have have been solved by nature. Your body has exactly the same problem with load balancing in terms of energy, in terms of chemicals that are being shipped around, and in terms of information. That's what the brain is doing for the body. Reinforcement learning actually is a very ancient part of the brain that actually is absolutely essential for load balance, for energy balance, for salt balance, and chemical balance. And it might be possible. We have cognitive radio now, and Simon Haken has been talking about cognitive power distribution based on reinforcement learning. So I think there may be solutions if we look at how nature has handled these problems.
I totally agree, and I think there's a lot of lessons to be learned from the feedback mechanisms and the control mechanisms that are there in our human body itself. Except, I would just point out, and I hate to be so crass in a public forum like this, but I call the grid as the human body without the bladder. There is no storage. And it has to be balanced in real time. So there are some differences. Hopefully storage will handle that to some extent, but storage is expensive.
So, and it's interesting you mentioned lithium-ion because Elon Musk is building this huge factory for building lithium-ion batteries. Everybody thinks it's going to be for his cars, and presumably they are storage devices if there are more electric cars. But, he could sell them to the grid.
Absolutely. In fact, there are partnerships being created between Tesla and SolarCity, which is the largest solar installation firm in the United States, residential installation firm. And Elon Musk happens to be in the chairman or board of both of them. So, yeah, there's a plan out there, I suppose.
More questions? Go ahead.
I can repeat it if you want.
So thank you very much. It's a very fascinating area that I think is new to many of us. How could we get involved, right? Where do we go and find data set that describes some of these problems? Are there any kind of open problems that you have released from either your university or any form of government-funded agency so that we can help?
Yeah, that's a great question. I would say that I think increasingly the utilities are willing to share the data. There's a privacy issue as well in this, but I know some of my colleagues at Stanford have gotten access to data, and they're analyzing it. I think there's a huge data problem that is, how do you got lots of data coming out from different parts of the grid. How can we create value from the data to the consumer, to the system, which is the utilities and the ISOs, et cetera. And I think there's a realization, and there's a question really we need to be asking on the electricity system today, where is value for you? And I think that is being done in real time as we speak. And that's going to happen in the next several years now. But I think when they see value, the data will be available. And the question then would be, how can we partner? And when I say there's a potential instability in the system because you can generate electricity lower than the utility, I think the utilities have to be part of the solution. And I think they realize that. Their business models have to change. Their financial models have to change. And I think that's what is going to happen in the near future. There's a university consortium of some kind that is forming and to do this. But I'm not sure, for example, that I think there's really the industry engagement in this is very, very important. But I would also say that there's a little bit of history out here. If you go to most electrical engineering departments and ask the question, how many professors are actually working in power systems? And the answer would be quite shocking, or maybe not surprising at all, that it is very, very few, a handful. And I think the new electrical power engineers have to combine with the data scientists who are in this room to figure out how to create that modern grid, because that's not going to be the 20th century grid.
Any more questions? Yes?
How about, I know that when you have central distribution and you start managing it, you start observing it down to the sub-second timescale, the dynamics gets very interesting, and there are runaways, oscillations and things.
That's right.
If you take by analogy the effort some years ago to scale up to the VLSI and beyond, analog devices everywhere, it was found to be dynamically very unstable, as well as leading to static properties that you wouldn't have estimated by looking at a small amount at one time. In the power world, is there an effort to understand the dynamics when the edge is a contributor to generation and storage?
Well, if you go to the power conferences or controls conferences, you would see that that is going on right now. Not to say it has not been done in the past. There have been algorithms, control algorithms that have been developed. Just to sort of highlight what you're saying, I mean, you're hitting right on the mark on timescale and dynamics. For example, if you're attached to the grid, you don't have to worry about frequency, you don't have to worry about voltage. They're controlled for you. If you somehow disconnect, those things go away, and the inertia of the grid, which has about 8 seconds of inertia, goes away. And suddenly, you can have voltage spikes that can trigger a relay, a circuit breaker, and then you can have a cascade of circuit breakers, and the whole thing shuts down. And that's the kind of dynamics that have to be controlled. And you have to do it with the right kind of control algorithms on the voltage and frequency, and to regulate it so that you don't allow those spikes to come. And that understanding is, I would say, being generated now. Those things are being developed and implemented right now. But it's not widespread. It's happening.
We got time for questions? Right, if not,
Great.
let's thank again Professor
Thank you.
Majumdar.
Thank you very much.
Thank you.
Thanks a lot.
That's great, thank you. The next speaker could come and set up.